Hi everyone, hope you're keeping well. Just wanted to try and talk you through the PowerPoint that I sent through on energy changes in endothermic and exothermic reactions. So the first thing I asked you to do before you started was to consider the different parts of the words that make up endothermic and exothermic. So the first thing to think about is that thermic word, where we might have come across that before. So therm, coming from the word thermal, which hopefully we recognise maybe from physics, being type of energy that we often associate with feeling hot or cold. So thermal energy store we often talk about in physics. Exo and endo, the prefixes there you might have come across maybe in Key Stage 3 biology when you're doing classification of different types of animals. So exo, we can use that word exoskeleton to help us. And then of course endo, we see that in the word endoskeleton. Now, endoskeleton is actually the type of skeleton that we are most familiar with, as it is the type of skeleton that we have. So with an endoskeleton, your skeleton is inside your body. So example being humans, dogs, cats. Whereas an exoskeleton, you see this a lot in animals such as spiders, and actually their skeleton is on the outside of their body. So with that knowledge, we can then consider what these prefixes exo and endo actually mean. So exo is to do with this outside, whereas endo is to do with being inside. So when we're talking about exothermic and endothermic reactions, we're talking about that thermal energy either going outside of the reaction or inside. So outside means it gets transferred to the surroundings, whereas inside means that we take energy from the surroundings into that reaction. So an exothermic reaction is where thermal energy is transferred to the surroundings. We get a release of energy. So if we're releasing energy to the surroundings, we're releasing that thermal energy, and what we'd then feel is an increase in temperature, because we're increasing that thermal store of the surroundings, and so the temperature is going to increase. Whereas with our endothermic reaction, our thermal energy is taken in from the surroundings. So if we're taking in energy, our temperature of our surroundings, if our thermal store is decreasing, then we are going to decrease our temperature. As that thermal store of surroundings is being reduced. So considering our exothermic releases energy to the surroundings and our endothermic reactions take in energy, so causing an increase in temperature for an exothermic reaction but a decrease in temperature for an endothermic reaction. Can you now think of any real life examples of exothermic and endothermic reactions? It might be something in your day-to-day life, or it might be an experiment that we've done before. Just want you to have a think for a couple of minutes, jot down some ideas of different types of reactions that you can think of, and then whether they might be exothermic or endothermic. Once you've thought about them for 2 minutes, there are then a selection of examples on the next slide of the PowerPoint. So I separated them into orange and blue. So orange we often associate with warmth, and so they're going to symbolise those exothermic reactions, whereas the blue is for the endothermic reactions. There are some that maybe you won't have thought of, such as respiration that happens in our cells, so linking biology into this as well, but also melting ice, so something that we're very familiar with, ice melting. That's actually taking in energy from the surroundings in order to do this, and therefore it's an endothermic reaction that's going on there. So when we're dealing with chemical reactions, we're often dealing with experiments that are in a solution. So a typical experiment would have your reaction mixture in a beaker, or we could use a more insulated polystyrene cup. We could use a lid to make sure that no energy is going into the surroundings. So we've got a nice insulated system with our reaction mixture going on there. We often would put this then in a beaker to stop the polystyrene cup falling over, as our beaker is much sturdier than our polystyrene cup. And in order to decide whether a reaction is exothermic or endothermic, we would measure the temperature of our solution using a thermometer. So in our reaction mixture, a temperature decrease would be an endothermic reaction, whereas a temperature increase would signify an exothermic. The way I always remember the difference between endo and exo is that exo has the X, just like in exit. So I always think of the energy exiting the reaction, it's being released to the surroundings. And in terms of our reaction mixture, this is our thermal store of the surroundings. So our thermal store of that reaction mixture is what is changing. So our reaction mixture temperature signifies whether that thermal store of the surroundings is being increased or decreased. Just label those other pieces of equipment. So the beaker, which is used to keep it stable, where our polystyrene cup, good for insulating. Same with our lid. And then our thermometer. Which obviously is measuring our temperature. So this next bit is looking at reaction profiles, and what they do is they're showing you the energy difference as your reaction progresses. So left hand side is always the start of the reaction where the reactants are, and the right hand side is your products where your reaction has finished. So our energy goes up the y-axis, whereas our reaction progress goes along the bottom. So two examples here are going to be our exothermic and our endothermic. So with our exothermic reaction, we know that we are releasing energy to the surroundings, whereas our endothermic, we're taking in energy from the surroundings. To make it comparable, we'll have our products, our reactants, starting in the same position. And so because our exothermic reaction is releasing energy, we know from our law of conservation of energy, energy cannot be created or destroyed. So if we're giving energy to the surroundings, our products must be lower in energy to compensate for that difference. With our endothermic, if we're taking in energy, we're needing more energy, and that's because our products are higher in energy. To complete this, in both cases, we end up with a hump. And this is because in each of these cases we still need energy to start the reaction off, and that's called an activation energy. So from your reactants line to the peak, is your activation energy. And this is the minimum amount of energy that is required for the reactants to react. The other arrow that you sometimes see on these is the difference between your products and your reactants. So here and here. So your downwards arrow is going to be a negative energy change, and that shows us that it's an exothermic because energy has been transferred to the surroundings, whereas our upwards arrow, this is a positive energy change, and so this is our endothermic, where we've taken in energy from the surroundings. Your next task is to think about what's happening to the bonds between water molecules when ice melts. So ice we know is a solid, and our water molecules look like this. So as a solid, nicely compact together, but as a liquid, they're going to be more spaced out, filling the bottom of that container that they're in. So thinking about what's happening between these molecules, so thinking about previous topics, looking at structure and bonding, remembering that water molecules are simple covalent structures. So simple covalent molecules, when we're melting, what's happening to be overcome here? Because our covalent bonds between our hydrogen and oxygen atoms, they're not being broken. Instead, what we have is some intermolecular forces between our atoms on our different molecules. So we need energy to overcome our weak intermolecular forces. So therefore, we're taking in energy from our surroundings, and therefore it's endothermic.